Good day, ladies and gentlemen, and you're all most welcome to today's presentation. I think there have been some changes in the clocks and so on, but I think we're all harmonized now, so we're ready to start. It's just it's 1500 hours here in Ireland, and it's 10 hours in Eastern Standard Time. So, my name is Ian Cowan from Dublin, and I've been tasked with hosting these meetings of the CNPS every 2 weeks. These are technical sessions. They were originally set up as alternative sessions to the main sessions, which are then held every week by David de Hilster. Now, these sessions we have in the past concentrated a little more on technical details, and we've had people going into details with regard to their own research, which most of us perhaps were not too familiar with. But I think the talks have gone fairly well up to now. We have a program which is petering out a bit now towards the end of the year, beginning of next year, but we still have a number of interesting lectures arranged. And if anybody has any interesting ideas, either on their own behalf or on behalf of others, they could maybe drop me a line, and we can see with maybe putting them in perhaps in the new year. Now, 2 weeks ago we had Mark Dorazio, I think might be his full name if I'm pronouncing that correctly. And he was talking about the work of Ernest Sternglass with regard to the essential constitution of all the multiplicity of particles that we have in modern physics. And so today, I think is a bit of a complementary endeavor. Mark has offered to talk about Menahem Shimhony, if I'm pronouncing his name correctly, and his work. Both of these gentlemen actually died in the last few years, so it's really secondhand interpretation of their work. But in particular, Mark has concentrated on gravity, the implications for gravity, which I think is spelled a bit gravity on the announcement to this. There's an extra I, and maybe that's a bit of a Freudian slip, but it's a very grave subject. And Mark will be talking about how, in his view, Shimony solves the problem of gravity in an amazingly simple way. So, we're all ears hearing about that. Now, I'm just keeping an eye on who's here. We have already a couple of comments coming in on the social media. We have quite a number of people. So I see Toby Grotz, who's worked with us. He's going to give us a talk in the coming weeks also. And in the, I have a private chat. Just if you bear with me, I'll just see what it says. Greetings, James J. Keane. You're very welcome, Jim. And we have Bob Gray and Dennis Allen. We have a gentleman, Jim Harford, whom I haven't heard of. He might have been invited by Mark. Now, what I was going to say while keeping an eye on the comments, Grave, Graive. I made a joke about gravity being spelled Graivity, from the feminine form of Old French gru, from the Latin gracchus, Greek, and thus thrush being a migratory bird that had hibernated in Greece. So Greek birdity. This fellow's being super facetious. Anyway, the reason I'm being a bit prolix in my introduction, your guest, Jim, is on Android Chrome, which has a bug that causes echo. Google is working to fix it. From now, please ask your guest to wear headphones to avoid echo or use a different browser. So if you had an echo, I'm not sure who that is, if it's Jim. If you have an echo, perhaps use headphones. So from my experience 2 weeks ago, our speaker actually didn't appear for the first 15 minutes, and we were a little concerned that he might not appear. So we had some improvisations. I think there was a lady who calls herself Fractal Woman, Laurie Gardee, who actually had some personal experience with regard to Sternglass's work, and she gave us a bit of an introduction. Now, today, let me just see who exactly here is here. Yeah, Jim O'D. I think he might be another invitee of Mark's. Mark's is not here yet, so I'm sort of expecting that he might appear in the next 10 minutes or so. But if so, we have a little bit to improvise on. Now, my first port of call for this is normally people in the green room, whom I'm sort of imposing upon to back me up. So it might be possible to have a pre-conference chat, waiting for Mark, in the hope that he will appear. I'm just keeping an eye because he can easily appear, and I can miss him, but he's not here yet. So may I just impose rather abruptly and rudely upon Jim, because I'm just interested, Jim, do you have any brief comments on how your own ideas, your binary mechanics, your own ideas, your own take, in particular with regard to gravity, might impinge upon any modern theories thereof?
Well, sure. I mean, we can start at the beginning. Almost 10 years ago, I wanted to disprove binary mechanics. I wanted to reject it, show that it's false. And it predicted that surface temperature was an important factor in in phenomena that we classify under the rubric gravitational attraction. And so what I did was I downloaded data. I wanted to show that this prediction of binary mechanics was false, and therefore the whole approach that I was pursuing at the time was inadequate or wrong, basically wrong. What I did was download data from a French observatory on lunar laser ranging and correlated that with moon phase. Now, when we have full moon, the temperature of the near side of the moon, that is with respect to Earth's position, is of course brightest and hottest because the surface of the moon facing us is illuminated more. And conversely, as the moon phases change and our view of the moon darkens to just a little sliver, I forget what that's called, that surface would be cooler. I correlated these phases, which is again downloadable data, and I had to write software to read the data files and do the correlations and so forth and plot the results. And what I found was, in fact, binary mechanics was verified that surface temperature of the moon did matter by some 10,000 kilometers of distance. In other words, in full moon and near full moon in those days, the moon was much closer to Earth than in when the moon was less bright from our point of view here on Earth. The moon phase, whatever that's called. And so basically the role of surface temperature in gravity was confirmed. In fact, the Casimir effect, which has to do with the attraction between two plates, which are very close to each other, is also temperature sensitive, so that on that rather micro scale, the same effect is seen. And both are predicted by binary mechanics. Why? Because and here I conclude this little lecture, if you will. The reason why is that there's a law of motion in binary mechanics that objects tend to move toward areas of greater energy density. And if the surface temperature of the moon is higher, there's a greater energy density in the space, adjacent to the moon, facing Earth, and therefore the moon would tend to move toward Earth. And so that summarizes it. Is that clear, or do you have any questions on maybe I left something out?
Well, no, it's most interesting what you're saying, and we could go into a lot more detail on this. In fact, we might even impose upon you to come back if we're not able to pursue it further today.
I could probably display the graph
Well,
on a share screen.
I mean, we're imposing upon you, but what you're saying is actually most fascinating. I didn't expect, this departure from maybe the specific aspect of Shimon's work. But I mean, if you have anything handy there, it would be most stimulating, even if we have to curtail it when the speaker comes.
Let's see if I can call up the paper. Let's see.
As you were talking about that, I was just thinking that the heat of the moon, I think that was first measured here in Ireland, actually, by the 4th Earl of Ross in the centre of Ireland, in Burr, Parsonstown. The 3rd Earl had discovered a spiral nebulae with his reflector telescope, but his son measured the heat of the moon in the way you're talking about relative to the phases and so on.
Well, that would be the surface temperature facing Earth. Now, the
Right.
net temperature of the moon does not necessarily change at all, okay? Because the far side of the moon would be cooler precisely when the near side is warmer. In fact, during all phases of the moon, half of the moon's surface is illuminated by the sun, roughly speaking, is it not? And the other half, whichever it is, according to the angle at the time, is not illuminated. So we're talking about no energy change or no temperature change, and if we relate temperature of the moon as a whole, okay, in the changing phases of the moon. So this also disproves general relativity, or excludes it, because if in other words, the effect that which was extremely statistically significant, I mean, beyond any doubt whatsoever, that this effect would not be predicted by general relativity, because the total energy of the moon, as reckoned by its, a volume average temperature, as it were, remains the same regardless of moon phase from the perspective of the Earth. So, needless to say, I was my effort to show a null effect, that is, to exclude binary mechanic theory, with this research based upon other people's data, lunar laser ranging data from a French observatory. And by the way, I'm rather surprised no one has replicated this. There's lunar laser ranging data from American and other observatories where one can match that with lunar phase and produce the same graph that I did. It's basically an ascending curve with the shortest distance between moon and Earth at full moon and near in the few days, near full moon. And this curve,
well, not necessarily the shorter distance, but it's just the phase, yes.
And this curve ascends to the greatest distance, at the darker phases of the moon. So this sort of eliminates general relativity, because there shouldn't be such a change there, because the overall temperature of the moon would remain the same. But I'm most intrigued by this temperature work that you referred to, how it might be relevant here.
Right. Well, that's maybe 150 years old. He was first doing it. But yeah, I sort of see what you're saying about the constancy maybe over all the moon, but maybe in particular, why do you say it contradicts general relativity? I mean, maybe it contradicts many other ideas, but why
Well,
would you say that?
if the overall temperature of the moon remains the same, there are plenty of folks in physics community, excuse me, that can relate temperature to energy content. Okay, with the so-called Boltzmann expression. Okay, so and those general relativists would therefore consider this energy content as a contributor to mass via E equals mc squared, as I understand it. And so therefore, if there's no overall temperature in the overall volume of the moon, surface and everything else, during the phases of the moon, there is no mass change, or that would be relevant to the attraction associated with the theory of general relativity. And in fact, even in Newton's theory, there would be no mass change either. And so both of these are sort of excluded by my data. So what we have then is the binary mechanics law of motion appears to be superior in predicting the results compared to both Newtonian's motion equations and general excuse me, and general relativity.
Right. Well, as I say, I'm just while I'm listening to you, I'm looking at some of the comments. More, yeah. Okay, just some comments come in. I'm just wondering. It's really the audience which needs to be consultant. I mean, it's more than 15 minutes into the talk, and we don't have Mark here. One or two people have asked about that, and I've tried to reply. But I'm just wondering, would the audience like to go into this in a bit more detail, subject to Jim's ability to do this, just without any warning at all? So, Denny, may I? Sorry, did you want to say something, Jim? Denny, you're mute. Can't hear you.
No,
why not let Jim explain this?
Sorry, say again.
Why not let Jim explain his?
Yeah. Okay.
Result?
Okay. And Bob, do you think that would be a good idea? Should we give Jim maybe, I don't know, half an hour or something to explain his theory, if he's able to do it, maybe with some illustrations?
Yeah,
the difficulty there is if we do that and Mark appears, I'm going to have to keep Mark off stage, because we can't just impose upon Jim and ask him to supply something just and then immediately throw him off.
No, I would not mind if I wouldn't mind if we go straight to Mark and cut me off. If you were to cue me, what I'm looking for is I'm going to paste a link to a video that I made on this precise subject. Okay, quantum gravity mechanisms.
A link. You're going to paste it into the private chat, are you?
Yeah, here we go. Let me copy that. This is one video. There's probably another one too. Let's see. Copy, and then go over here. Paste. That's the link. Oops. That's quantum gravity mechanisms, and it's sort of on topic. I don't recall whether or not that actually covers the lunar laser ranging experiments let's see if there's another one here. There's also papers, which, I could share screen and scroll through the papers.
Okay. Okay, let me see. There's a video there.
That's it.
I wonder should should I, or should we show that? How long does that occupy?
Well, if you went to that video, it should say right on the screen how many minutes it is. It's probably
Okay, I'm in
15
it
minutes.
now. Yeah, wait a minute.
It probably says 50. The 20
Funny enough,
minutes, 15 minutes, or something like that.
it just has 0. Maybe I have to start it. Doesn't seem to. Oh, 6 minutes. No, I'm looking at the wrong thing.
Well, all of my videos are less than mostly 15 minutes or 20 minutes or something like that.
Okay. Well, should I show this now?
Yeah. Well, the big thing that I might emphasize, Ian, which might interest people beyond even the question of gravity, is what I found myself saying a few moments ago. I hadn't actually gone officially to the point of saying that binary mechanics law of motion actually is a step beyond and sort of replacing to some extent Newton's laws of motion, which is quite a dramatic, possibly controversial statement to make. But and so in that case, maybe we gin up some interest and say, well, let's look at this law of motion, which I think is explained in the video, and chat about it or argue about it as the case might be. Basically, I hope to gather a little sympathy because my whole work with the lunar laser ranging using other people's data, okay. This is like a multi-million-dollar study when you consider all of the expense of the lunar laser ranging data acquisition and so forth. So it's based upon other people's data, and I wrote the software for rereading the data and cross plotting that to the lunar phases, and that's about it. And it unfortunately, I failed to disprove binary mechanics because it was an outrageous position or proposition that actually surface temperature was the key to understanding gravity and not the overall mass of the objects. Okay.
Okay. I'm terribly sorry. I was about to say something about problems with that video, but I've just received a comment that Mark Creekwater is here. Why am I not
Great.
on? So, but he hasn't logged in. So I'll have to say, have you not logged?
Dennis says yes. Let's see Jim's video.
Yeah, no. What I was about to say is I can't start it, and neither can Bob Gray. So I fear there's a problem there, which I was going to ask you to sort out. Maybe you show it, and I was going to give you the screen. But Mark has now come in. Have you not logged in to natural philosophy.org? Okay. No, I'll do that now, he says, Mark. Okay. Because he's not in the green room. He has to get into the green room. Well, if hopefully Mark comes in the next couple of minutes and I bring him up and so on, maybe after today's presentation, we could impose upon you to give this more thought in the light of what Mark has said and in the light of what your ideas are. And maybe in the future, you could give us a talk on this, the implications of gravity for your own analysis, Jim.
Sure.
Yeah. No, thank you for being so patient. I mean, you're willing to come up and you're willing to be kicked off. Thank you very much for that. You're very generous and handsome in that. Presumably the word. Yeah. Okay. He still hasn't come in. Let me see now. Okay.
Because I loaded I'm loading
You're echoing a bit now.
The paper that has the gray, that it is.
Okay. Well, just while I'm typing this in, the link you gave, unfortunately, the video doesn't seem to be starting up. You appear to get something. It doesn't give the time. You press the play button and nothing happens.
Oh, really? That must have been corrupted. Well, I have another link. Let me give you another link. Plus, I have. Okay, here's on Rumble. Let me copy that. Control C. Go over to here.
I'm going to do it in the private
Control
chat.
V. Oh, okay. I just put up another link on Rumble. Quantum gravity mechanisms, HTML. Let's see if that will play. Or I could share my screen and try to get this graph, because this was the graph. This is a sort of a make or break thing about almost 10 years ago, where I had formulated binary mechanics and published a few papers speculating about its relevance and so forth, and tried to disprove. Tried to disprove these postulates of binary mechanics, and
okay. Yeah, that link works. Bob says. I just couldn't understand myself.
What it does do is question the applicability of Newton's laws, and as well as of general relativity. And since a lot of people here seem to favor the classical mechanics, the Newton's laws, they might want to, try to shoot me down on that. Which if you can, I would be most grateful. But apparently, whatever binary mechanics predicts seems to be borne out by the data so far.
Well, it's a very scientific endeavor to follow the lines you have. Actually, Charles Darwin said that he always sought out works which contradicted his own and studied them in the greatest detail, because that was a way of testing his theories. I think if I may dare to say that frequently modern science is the opposite. One just ignores things that contradict one's preconceived ideas or the mainstream ideas. Oh, there must be some nut case. I won't even bother look at that. So you must always try to check on things. I might just bring Jim Harford up for a moment, because I don't know if his mic is muted. I don't know if he's related to the speaker or Jim Harford.
I'm not sure if the mic is working correctly.
Yeah, I can hear you now.
Okay.
There's a bit of an echo though. Me. My voice is probably echoing.
Yeah, I'll try to make it clear. Is that better? Maybe I'm too close.
Well, we can hear you. Yeah.
Okay.
No, I'm echoing if I speak.
Oh, I see. Yeah. I met Mark years ago at the Princeton Public Library. He had just arrived from a walk from Arizona, and I noticed him with his computer, and he showed me his book, as he called it, in a printed form, and he was working on a Chromebook where he had the document and was working on it, and I thought he was quite fascinating. As I say in the chat, he had previously been known as the purposely houseless professor. You can look that one up, Mark Dorazio, and it's an extraordinary story. And I sensed that he was going to need a few other libraries to do his work, and I introduced him to I recommended that he go to the Institute for Advanced Study and deliver his paper there, and ask about the book Turing's Cathedral while he was there, and see if he could read it or get a copy of it. And he did, read it, and I immediately sensed that this is a person who devours information and knew all kinds of things. He was dead set on seeing Einstein's house. I said, why don't you leave those poor people who lived there alone and aim for his office, which is described in that book, Turing's Cathedral. And we did get at least to the door of Einstein's office. In that time, he did endear himself to the librarian at the Institute for Advanced Study, and his paper was put on the shelf. She said, I will put this paper on the shelf. And if anyone knows what the procedure is there, if a paper winds up on the shelf, somebody must read it. And evidently, Freeman Dyson did. And Freeman Dyson was evidently, they shared office space, I think at Cornell. I'm not sure. They were, they knew each other. And I just, in my encounters with Mark for the winter, and he lived in Princeton in a self-built wiki hut just down from the Fine Hall, which isn't the original Institute for Advanced Study, but it has the name of the original Institute for Advanced Study. And it's the math building, and he spent a lot of time in the basement there looking at books, and devoured all kinds of books while he was living in Princeton, aiming to get to meet Sternglass, because he knew that Sternglass was still alive, and he wanted to pay his honors. There's an article about him after he left Princeton in April, and he lived in a pine grove outside of Cornell, and was able to meet with Ernest Sternglass. What I don't know if he's ready to talk, but just I mentioned in the chat that he did get a response from Freeman Dyson. Freeman Dyson read the paper, and I was there at the Lewis Library, which is the science library at Princeton, and I heard a ding on Mark's computer, and sure enough, there was Freeman Dyson's response, and I will never forget it. It said, I know Ernest Sternglass. I don't like his math, but the world needs heretics. I thought it was a beautiful statement.
You can discuss it.
So I just thought you would enjoy this story. I enjoyed, I think it's Lori's, the fractal person. I enjoyed her story from your last recording, and I'm just so glad that you've given Mark a platform for eternity. So that's my story.
Well, thank you very much for that. It's a bit difficult. I might actually bring you down because you might get rid of the echo. Yeah, that's got rid of the echo. The echo is going into your own system, Jim, and maybe coming back. We can sort that out if necessary. But thank you very much for that. It's great to have somebody who is connected with Mark and is able to supplement some of the information. Indeed, as Laurie did 2 weeks ago. But I was about to ask you, were there any specific aspects of the work, maybe of Shimony this time rather than Sternglass, related to gravity, or indeed Mark's thesis that he had actually solved the problem of gravity, whatever that is, in a simple way? Is there any possibility that you know anything about that and maybe could speak for 10 minutes on it? could we impose that upon you?
Okay, you did fix the sound for a moment. I don't know if it's now working again, but
Hello. I think it's working. No, still an echo.
Let me see.
I don't know.
Back, is that better? I don't know.
No, when I speak, coming back at me.
Okay.
You're not any times logged into the social media as well as the green room.
I have Zoom on, but I don't think it's connected. So,
Because if you go now over Facebook or YouTube, it's a delay because they're not quite simultaneous.
no, I have a really bad internet connection where I am. So,
We can hear you perfectly.
Right. So anyway, I'm lucky to be here at all. And with Shimony, I mean, I have another. For me, the encounter with Mark was mysterious, and it was spontaneous. It was spontaneous. I am not a mathematician. I'm an audiovisual guy who's retired, and just I lived in Princeton at the time, and I knew Princeton really well, the campus, and I really shared a great time with Mark in that period. My only anecdote about Simhony was, I'm trying to remember a scientist's name who worked for RCA, who was a friend of Einstein's. And I tried to get him involved with, reading Mark's paper, and he said, no, this is math that's way beyond me. And he goes, I knew Shimony, and it's all of this is way beyond me. So, can I speak on this? I can at this moment. You're looking at an Uber driver. And an Uber driver who still shows up at the Institute for Advanced Studies, picks up mathematicians, and is able to talk about gravity waves and all sorts of things, with a half-baked idea of what it is. I did tell Mark when I saw him, I said, well, they're introducing a lecture about gravity waves. They evidently found them. What this has to do with Simhony is only it's about gravity, and we went together and sat at the institute, listening to people talk about the proof that the gravity waves exist, and afterwards we walked into the institute woods and Mark was saying, well, they got it all wrong. It wasn't two black holes coming into one, it was actually one going into four. And he predicted, if they knew at the time they had only two signals. I think now the recording devices, there's three on the planet, and they can pinpoint where a gravity wave is coming from. He said, well, he did the math and said, if the sizes that they said were true, you can prove that there's going to be another gravity wave in 43 years. That was his conclusion while we walked. I don't know any of this. I'm just repeating words that I heard. I'm amazed that I can even hold a conversation about gravity waves with some of these mathematicians. And that's really all I know. And I hope that he's on now so that he can speak. And I've given you a little bit of what I know about him. And I posted a Vimeo. I recorded him and posted it on Vimeo because it was inexpensive and it was a high quality. So there's a starter video of Mark in the chat.
Okay, I'll bring it down while I'm speaking. Thank you very much, Jim, for that. It's background information which I think will be of interest to all of us. It's been extremely interesting for me to listen to you, and we'll hope to bring you back maybe when we have a bit of discussion after today's proceedings. I'm not quite sure how that will pan out because Mark is not here yet. And in fact, I think what we should do is we should invite Jim Keane back because he's got his system up. Well, wait a minute now. I was going to let him share his screen and put the video, but you've posted something there which I'm adding up. Well, what is that, Jim?
That's the gravity increased by lunar surface temperature differential, the lunar laser ranging study of 2011 that I started talking about.
So do you want to talk further about that, or do you want to show the video?
Well, either one. It starts in a way with my attempt to disprove binary mechanics postulates by analyzing this data. And it turned out that binary mechanics was in fact confirmed, and this draws in, and so this supports the motion law defined by binary mechanics, that objects tend to move toward areas of greater energy density. So I'll let you decide. If you want to just show the video, that's fine. You don't have to put up my shared screen. You can click it. It's better if you click it there on your end. Or I present this paper because this paper basically in 2011 was my effort to either stop working on binary mechanics, although I had put a bunch of years of effort into it, or continue. And I chose what I thought was the most outlandish hypothesis of binary mechanics that I had on hand about the effect of object surface temperature on gravitational phenomena. And it turned out that binary mechanics was right, and my effort to prove that it's not right failed.
Right.
Now, if anyone can poke holes in this data, I would be most grateful, for example, because a lot of my subsequent work in binary mechanics was based upon the fact that one of its most outlandish predictions proved to be correct.
Okay. Well, the only thing is some people may say, as with a lot of modern scientific theories, that it doesn't necessarily prove that the theory is absolutely correct if it makes a correct prediction. Obviously, what you were trying to do could have disproved it if it came up with an erroneous result.
Yes, I agree with your whole statement there, Ian. You're absolutely right. We're not talking. I guess it's a little bit taboo to say we're proving a theory or
Right.
proving postulates. So I agree with you on that. What I am saying, I guess, better stated, is that the postulates, the predictions that arise from the postulates, seem to be borne out by observation and data.
Well, I'm wondering.
I think the video includes, I don't remember exactly, but I think the video includes this paper and pictures from it. So it could be that the video is going to both. I know the video does explain the law of motion in binary mechanics.
Well, why don't we have a look at that?
Okay.
But unfortunately, we can't get it up at the present time. So could I ask you to show it? I'll share your screen and show it. I'll give you all the authorities and I'll bring myself down. So you know how to do that.
Well, let's see here,
Jim. At the center of the bottom banner. Let me see now. It should say present.
Oh, okay.
And it might be your screen.
Yeah, I'm presently sharing my screen right now, showing the paper. But if you want me to show the video we can try that. I'm going to it right now, and I'll click on it. Here it is.
And the way you're doing this gives me a little box which I have to bring up. So in other words, I've brought up these this presentation. If you succeed in doing it in the video, I'll bring that up as well.
For some reason, I can't get this video to come up.
Another way is to put it, say, on your desktop or something, and then say share. Well, you can either share your screen or you can share the video file and then search for it in your system, say on the desktop.
Well, it looks like I can't play the video. You can't play it from the link that I put in the private chat?
It doesn't seem to be playing, and Bob had the same problem. I'll try again now. I have it here in front of me, and when I press the play, loading. Maybe it says it's loading now. Oh, sorry, it's working now. Yeah, it's working.
Did you try the Rumble one?
It's working now, Jim. So I should be able to do it. So I have to share my own screen. Let me just see, because I was assuming as moderator you could see everything. Of course you can't. So let me just.
Oh, I think I can't do it because I don't think I can play it
because
it requires audio, and StreamYard is using the audio, and so that's why there's I can't play it while I'm on StreamYard.
Oh, okay. Well, let me see. Can I do it? I'm trying to share the screen because I don't actually have the video here. Select tab, entire screen. Let's see what happens now. Okay, so you can probably see my screen now. Let's see, get rid of that. I want to get rid of it.
Well, I can't play the vid there.
No, but I can play it. But I think I got rid of that. I just want to.
If you can play it, then yeah, we're good to go, because apparently, on the way my computer is set up, if the audio is being used by StreamYard, it refuses to play an MP4 file, which is what I was going to attempt to play.
Yeah,
which is very inefficient, because I'd be sending you MP4 images, which you'd have to retransmit and so forth. It's better you do it from the home base, as it were.
But can you see the video BitChute up on my screen now? No. Are you still there? Maybe. Sorry, no sound.
I see my screen being displayed. If that helps.
Yeah, BitChute. Is that what you say? With
well, I put a link in the private chat to the BitChute link, and I also put a Rumble link for the same video down below in the private chat. Apparently, you can click on either one of those.
It's the window.
This technology is something. Imagine screen. Even 5-10 years ago, we couldn't do any of this.
Yeah, when it works. Oh, well, that's
and I
true.
should have
put
a nice shirt on. I didn't know that.
We're not familiar with it.
I'm wearing my old rag T-shirt.
Well, I couldn't physically survive being here in a T-shirt because the temperature's gone right down, to a few degrees above zero here. Although I do have some heating. Not very much. Yeah, I don't seem to be able to get rid of this entire screen.
Now, previously you have done this, so success is in the offing, Ian.
Yeah, I know. Well,
previously you have shown from the internet one of my videos.
Yeah,
and you managed to do it, and.
But see, it may have been that you put it up.
No, actually,
that. But whatever you did for the slide there. In other words, if you share a video and then say the video is on the desktop, forget about the fact that the system doesn't like you sharing MP4 audio. Just put it up and I'll have it here as a box, and then I can actually.
Well, I get a program error message. I cannot start the video.
I don't want you to start it. I just want you to put it up. Anyway, I don't
Let
know
me
why,
see if I can.
Did you give a link to that? That's the other way of doing it. But that didn't work.
I gave 2 links, one for Rumble and one for BitChute. If you scroll near the bottom of private chat is the Rumble link.
Yeah, I see that.
And the other link. So if you're able to
click on that. Yeah, this is what I have. I've done this already, but I'm just having difficulty sharing it with you all, which is annoying. Let me see what's happening here. I mean, I should be able to do this. Whatever about you, as moderator, I should be able to do this. Present. See, I'm trying to share my screen, but it doesn't seem to be working. Wait a minute. Wait a minute. Yeah, I probably share. I'm getting somewhere now. Can you see it now?
The binary mechanics system state.
Yeah, but you're playing the wrong video, I think.
Am I? Oh.
Function.
Okay.
Final score bit function 2 wave function 1.
Talking about quantum gravity,
both position and momentum. The wave
That's the wrong one, isn't
lost by system state representation, position, or momentum, not both simultaneously.
Yeah, you're not playing the gravity one.
Stadium.
Okay, let me try to play that one. I want to get rid of.
Oh, wait.
Celebration.
Sorry.
It said that their wave function would win easily.
Is this all right
These
now?
adherents to the legacy quantum theory have been taught for decades that their wave function was invincible. They thought their wave function.
You seem to have stopped something there. Okay.
Okay. In the Windows Media Player, apparently I can play a video.
You can. Well, I can do this again. I had 2 videos.
Yeah,
up and
I can play the video. I was playing the wrong one.
Where were you?
That was funny. But now I can play this one. Let's see.
Was going to win. To summarize, in quantum mechanics based upon continuous space-time theory, the system state is modeling all points representing position without momentum or momentum without position. On the other hand, binary mechanics.
I'm trying to get it to play this video.
We can hear it, but maybe not see it. Now here's something. I'm sorry to it's sort of like
here it is.
Hello,
I got it.
Force majeure.
Talking about quantum gravity mechanism.
Now all I got to do is share my screen.
A motion.
Yeah, you do. Yeah.
Oh! Now is share the screen.
Oh, wait a minute.
Okay, I'm going to share the screen now. Let's see.
Yeah,
because I'm able to play my MP4 file, but of course I'm transmitting the. I've got so if I share screen, you should be able to see then that video. It would be better, of course, if you played it at a central location as the host, as opposed to me trying to but I now have a fiber optic internet going here on the wonderful island of Dominica in the Caribbean.
Yeah, we envy you. That's why I talked about putting a heavier apparel on.
So we have state-of-the-art technology for internet. So I can try to. I'm going to share my screen again if you want to be in. Ian, if you can't.
Well,
play.
I just think
okay. Here I got it.
Can you hear me, Jim?
I can put that there and
Let's
start.
see if you're hearing me.
Should I start here?
Can you hear me, Jim?
I can hear you, Ian.
Oh, okay, because I'm saying
Yes,
a
I
few
can.
things which are okay. They're quite rude. They're counter to what you're saying, and they're contradicting you, and so on. And I'm sorry about this. We're almost getting there, but I'm getting comments in. I'm trying to do a few things at once from Mark, maybe via his wife or somebody. I don't know, Sue. And I think the problem is that they have logged into this generic link, which unfortunately doesn't seem to have been updated. You might remember this, that sometimes if you use that generic link, you got last week's presentation. I think that's the problem. So I'm trying to solve it with them. I've given them what I think is an up-to-date. Yeah. So I'm sorry, I'm not giving you my full attention. I'm giving you partial attention, and I'm also trying to resolve this problem with who was... Mark is here. It's worked, Jim. So would it be all right if I profusely apologize?
Okay, great.
I thank you for your efforts, and we'll come back to you. We're not going to forget about all this. Would that be all right, Jim?
Okay.
Thank you.
Of course it is, because Mark should have, is in the spotlight today.
Yeah, you're
Welcome,
a gentleman. Thank you. So, Mark, better late than never. You're hiding away from us, Mark.
The problem was I never signed up as a member of the society, so I had to do that and get a passport and everything, and that took about 15
I thought the link we
minutes.
gave was obsolete. I thought that was it.
Yeah, and the link that I had was to last week's. I didn't have the link to this week's.
I think that was a problem as well.
Okay. Well, I'm glad I finally made it. Let me show you what we're going to do. This is about Simhony. Now, you guys can write down this information if you want. And I discovered Simhony's work on the internet about a year after I discovered Sternglass's work. And most of it is on the internet. That's where I found it. Even though he wrote 3 books, it's mostly on the internet. And you can learn everything you want to know about Simhony's work on the internet. And really, all you have to do is Google the word Epola, because Simhony made up that word. So if you Google the word Epola, E-P-O-L-A, which is short for electron-positron lattice, that then Simhony will come up and you'll be able to learn all about Simhony. I want to keep reminding you to read my essays. I'm especially proud of the one about the Larmor precession, so I'll put this information up so you can copy it down and look at it if you want to later. And so if you want to copy that down, I hope you will, because, it's all just simple high school algebra. And yet, for some strange reason, the people who have built the standard model have not figured it out yet. And even though I send emails to them regularly, none of them seem interested in reading about it. They just assume that I'm a crackpot and can't possibly know what I'm talking about, because it doesn't agree with the standard model. Well, so anyway, I hope you'll want to read that. So the main thing about Simhony's gravity model, gravity doesn't pull, it pushes. Maxwell was actually working on a theory very similar to Simhony's. And the interesting thing is, you can imagine that Maxwell might have come up with a theory very similar to Simhony's theory 100 years sooner If only he had known how small the atomic nucleus is compared to the atom. Now, I think most of you know if the size of the atom were a football stadium, the nucleus would be about the size of a golf ball on the 50-yard line. That's how small the nucleus is compared with the atom itself. Well, this was not known until Ernest Rutherford discovered it in 1911, which is after Maxwell died. But if Maxwell had known that, he might have come up with some theory, a gravity theory similar to Shimony's. And Shimony quotes Maxwell in his work in a frequently asked question, number 5, I believe it is. He says, he quotes Maxwell, which was published in 1864, saying that if we look to ether as the cause of gravity, it would need to, the ether would need to have an enormous intrinsic energy. His exact words, an enormous intrinsic energy. And he couldn't see how this would be possible. So he says we probably can't look for ether as an explanation for gravity. Well, Simhony has found a way for the ether to be very dense with immense intrinsic energy, as Maxwell knew that it must have to be responsible for gravity. And the way that this works is because the elements which compose the electron-positron lattice are so small and so close together that their density is about 10 billion times that of water. Ordinary matter, the density of the electron-positron lattice is about 10 billion times greater. Well, if it's that dense and everywhere in the universe, then how can we even move? Well, this is because the size of the distance between the elements which compose the epola is just the right size to allow the nucleus of an ordinary sized atom to enter. I've made videos about this. They're posted on Vimeo, Vimeo.org or .com, and where I explain this. And when the nucleus of an atom goes into an epola cell, well, you can imagine if it's the electron-positron lattice is a perfectly cubical formation like table salt. You can imagine that there's tiny little boxes with the distance from here to here about less than 10 to the minus 12 centimeters. Well, you can imagine when the nucleus goes inside one, it disturbs the electromagnetic forces which hold the lattice in place. And by disturbing them, it weakens them so that the lattice is weaker at that point. So that actually the particles that compose the lattice, they actually back off a little bit. The box expands when the nucleus of an atom is inside it. And this is the explanation for gravity. Because where you have a moon and a planet, the epola between the moon and the planet, and the epola where the moon and the planet are and between them is slightly less dense because the boxes expand. So it's slightly less dense than the epola which surrounds the two objects. So they gravitate towards each other. That's all there is to it. Very simple. That's Simhony's explanation of gravity. And I believe that this is the correct explanation because it's so simple. But the main thing you have to be able to understand how Simhony's theory works is that the little boxes, the little cubic shaped boxes are just the right size for the nucleus of an atom to go in between them. Now, if the atom's too large, then it's harder for the atom to go in between to get inside one of these little boxes. So that's why atoms like uranium and plutonium, they'll split in half because they're so big. They're not comfortable going inside the, in and out of the little boxes which compose the Ebola. And I hope that makes sense to everybody. Let me change the sign here, show you the other side. And then I guess we can open it to questions and answers. So I guess you can all see that and copy that down in case you want to read it later. And now, are there any questions?
Okay, well, are you more or less finished with the presentation so we can?
Yes, that's all. That's all there is to it. There doesn't seem to be much more. That's all you need to know to understand how gravity works, according to Simhony.
Okay, so basically, he is attempting to rectify the situation whereby Maxwell said that it would require such enormous intrinsic energy that it couldn't be principally. He's trying to, clear that up, and of course,
he figured out a way for that. Maxwell couldn't figure out how that would be possible, but Shimon figured out how it's possible for the.
Okay, so we may want to go into that in a little more detail as to exactly how he did that, and also your central thesis seems to be that when you consider Larmor precession as introduced by Larmor, that indicated an essential connection.
Did you read it? Have you read it?
Larmor precession.
Have you read my essay about it?
Probably not.
You definitely should. And when you read it, be sure to read the last appendix, the last part of it, Appendix D. That's
so is that in the reference there that you have?
It's the other one. The other one I had on earlier.
Okay.
One I had on earlier.
Okay. Okay. So we can open it to question now. I'll just check through the comments first before maybe. I think Jim has a question there and so on, but there've been a lot of.
Yeah, good to see Jim again.
Yeah. Okay, that's good. He's a fairly regular person, and actually, if you do take the liberty of looking at the recording of this, you'll find that for the first hour when we were so
I know. I saw that. I was able to watch it all. I just couldn't get on.
Okay. Well, Jim got us out of a hole there, really, because I was waffling on a bit, and he was introducing something which I think could be the subject of another lecture. But people are bringing in things like Ritz and Walter Ritz, pointing vector, EM fields. He's going back to the lunar temperature effect that Jim was talking about. That's maybe for another day. Yeah, let's see anything else here. Okay. If gravity pushes into the ether, is the ether also involved?
Is what?
If gravity pushes, is the ether also involved? And then he says,
yes,
what is
the ether? The ether is what pushes. The ether is responsible for gravity. It pushes on. If there were no matter, ordinary matter in the universe, the pressure of the Ebola, the lattice, the electron-positron lattice, would be equal everywhere. But because there is ordinary matter, it distorts the epola wherever it is and makes it a little bit less dense. That's what gravity is. It's the surrounding epola is more dense, slightly more dense than that's why gravity is so weak compared with electromagnetism. It's because it's only slightly more dense than the intervening epola between the two planets.
Is that a fair comment, would you say, from Cornelis? It appears to be similar to buoyancy.
Similar to what?
Buoyancy.
Buoyancy? Yeah, I would. I never thought of it that way. That's a very good analogy.
Okay. Very good. Now, okay. I think, yeah, epola is electron positron lattice. What is it short for? Lattice array.
What is the source?
Epola is electron positron organized lattice array. Is that what it stands for?
Yes.
Okay.
It's has the same structure as table salt, but much closer together, about 100,000 times closer together than the sodium and chlorine atoms in table salt. And also, Shimony says it's electrons and positrons alternating. Well, I modified Shimony's theory to say each one is an electron-positron pair. They're identical. They're bosons. And this agrees with Higgs' theory. Higgs is supposed to be a boson. So perhaps the Higgs field is another name for epola. Perhaps they're two words for the same thing.
Oh.
Yeah, Higgs boson, they're bosons. The electron-positron pairs that form the lattice, according to my modification of Shimony's theory, they're bosons. Each one is a boson.
Okay, well, since we've absorbed a lot of time, very usefully, I might say, even in your absence, Mark, we don't have that much time left. So I think it's probably time to start inviting members of the green room to come in and perhaps have a discussion. Now, I know if any of you want to raise his hand, I'll bring him up immediately. But Denny is doing that, so I'll bring Denny in.
Mark, if there's this rigid lattice throughout space, or fairly rigid lattice, how can it be true that an object that is in motion in outer space will continue in motion?
That Shimony deals with that. He says that when a moving object goes into a box, the box expands, and then when it exits the box, as the box contracts, it pushes it a little bit so it doesn't lose any speed, according to Simhony. It's like what do you call it? Superconductivity. An object will just continue through the epola like electricity through a superconductor without losing energy, essentially. Some people, I think Practical Woman visualizes it as a Bose-Einstein condensate, which might be one analogy to visualize what's happening.
Okay. I mean, Jim, whom I'll probably bring in a few minutes, he's asking what is the box? What is the box size?
Its size, Shimony says it's 4.42 times Fermis, and I modified Shimony's theory. If you read my essay, you'll see why. I forget which one it's in, but I modified it to say it's almost twice as large, based on theory, and that works because if you take a box that's the size that I give and calculate the volume of the box and the size of the particle that'll fit exactly inside the box. It's one of those particles that I described last week, the Sternglass cosmological systems, which each one's an electron-positron pair orbiting around each other at the speed of light. The one that's just the right size to fit inside my modification, the size that I give to the bow, is just the right size to fit inside the box. It has the energy of the Upsilon Mason, which was discovered in 1977. That's one of the most interesting results that I've gotten that sort of proves that my value is correct, whereas Shimony's value is too small. So you have to read the paper. I think it's the one about theoretical work of Sternglass and Shimony, by Sternglass and Shimony. I think that's the one.
That's your own paper.
Yeah, the one that I wrote. I described how the size of the cosmological system, that just the right size to fit inside one epola cell, is has the mass of an Upsilon Mason.
Okay.
Which is quite interesting. So there's no such thing as an Upsilon Mason. It's just a resonation of the box when high-speed electrons hit it. They think they discovered new particles, but they're not really particles. They're just little blips of energy.
Okay. Right. I'm just checking some of the comments. So, Denny, anything further at this stage?
Well, if it seems like if like a billiard ball or something was traveling through space, so the billiard ball would impact the positron electron pairs and would slow it down.
What do you have traveling through space? Anything? A proton?
A billiard ball, say.
A billiard ball?
Or something like that.
Yeah. Traveling through space.
Yeah.
I don't think it's not going to slow it down, because the ordinary matter is very thin and wispy compared with this stuff. It's like fishes going through a fish net with large holes in it so that all the fishes go through. That's how a billiard ball travels through epola. Each of the nucleuses in the billiard ball is just the right size to go through the epola without slowing down, like I described earlier, like superconductivity through a superconductor, electricity through a superconductor. And that's why the billiard ball doesn't slow down.
Yeah, but if the billiard ball, even if there was only a small percentage of the atoms of the billiard ball impacting the positron electron pairs,
it's not gonna impact them. They move out of the way. Each one moves out unless it's traveling at nearly the speed of light. That's why you get the relativistic increase in the mass, because it slows it down. It's harder for the electron-positron pairs to get out of the way if the object is moving at almost the speed of light. That's why the mass doesn't really increase, as the inertia increases. You get a kind of a drag.
That's right.
It's harder for the electron-positron pair to get out of the way if it's going real fast.
But why does it get out of the way? Does it have some psychic ability to?
It's electromagnetics. They just as a neutron approaches, everything has a magnetic field. They just feel the magnetic field and they move out of the way.
That's it.
Mm-hmm.
What speed is it going approximately? What percentage of the speed of light?
As what? A billiard? Anything? What we were talking about. A billiard ball? It can go any speed you want. I'm just using that as an example.
Okay.
The protons that come through cosmic rays, the cosmic rays are mostly protons. They travel at almost the speed of light, and billions and billions of miles without slowing down, even though there's an ebola there. All the stuff gets out of the way so that the protons travel at almost the speed of light without slowing down. Now, to give that much energy to a proton, you'd need a particle accelerator, several light years long. It's way more, those protons are moving way faster than any scientist can ever accelerate a proton to. And yet they travel through the ebola, they hit the upper atmosphere and called cosmic rays.
Okay. Right. Anything further you'd like to address to Mark at this stage, Danny?
No, that's fine. Thank you.
Yeah, I know you personally have done a lot of work, related to this, both on yourself and with the late David Bergman. So we may come back to this at a later stage. We'd like to hear.
Oh, I just thought of something else. Let me just say this briefly. The late Ian Montgomery, who many of you probably remember, we had a long email conversation one time where he said that the ebola wouldn't be stable because of Earnshaw's theorem, and I found the mathematical formulas for magnetic moment. They're very complicated depending on the angle between the two things and the orientation. Very complicated formulas. Some of them are strong and some of them are weak. And I used that on the lattice trying to figure out a structure that would, trying to work it out mathematically how it could be stable in spite of Earnshaw's theorem. I never could get it. We spent weeks on that conversation. He could never disprove it, but I could never prove it. So, like Fractal Woman said 2 weeks ago, it might not be cubical. It might be tetrahedral or something like that. But whatever it is, I think it definitely exists, and it's ether-like. Shimon doesn't like the word ether because it makes you look like a crackpot. And
I think Laurie mentioned that the last time.
Yeah.
Well, actually, this tetrahedron business is one of the questions which Jim has. He has a series of questions here. What happened with the tetrahedron shapes? So perhaps I'll bring up Jim just to give his general take on this and maybe address a few of the points he made in the chat, which I haven't addressed. You're back again, Jim. And you had a number of points.
Oh, hello. Hi, Mark.
Hey.
Nice to have you, Mark. Yeah, well, it's if I remember right, 2 weeks ago you were talking about tetrahedron shapes, and now we're talking about little boxes.
Yeah, the tetrahedron
did I miss something there or misunderstand something?
The tetrahedron is the shape of the proton. According to Sternglass, it's the shape of a capital H, but according to me, instead of a capital H, it's a tetrahedron. Yeah, it's the simplest three-dimensional solid. So naturally, Mother Nature would use that to build protons and neutrons, in my opinion.
So how do
Sorry, we seem to have lost you
these
there.
little boxes then?
The protons go in and out of the little boxes. That's interesting too. Imagine a tetrahedron inside a cube, at the center, a tetrahedron at the center of a cube. Each of the points on the tetrahedron is an electron-positron pair. So each of these 4 electron-positron pairs is interacting with each of the 8 electron-positron pairs which compose the cube. So they're interacting, and it's much too complicated to work it out mathematically, but you can visualize that they interact.
Okay, excuse my admitted ignorance of the details of your work, but how does, for example, an electron-positron pair know, is it part of a proton or some other particle or part of the Ebola or Epola?
Well, I'm sure they
Excuse me.
don't know. They don't know, but they don't need to know, do they? Why do they need to know? As long as they interact according to the laws of physics, they don't need to know what they're part of.
Well, you might say, what gave rise to there being one rather than the other? I suppose that's a bit more like cosmogony than particle physics. If they're all made of the same elementary.
Yeah, that's what Sternglass says, that there's nothing in the universe but electrons and positrons. And I think Simhony might agree with that. I'm not sure.
So you're saying that electrons, these electron-positron pairs, form a lattice, which we call the Epola, which is sort of like, I guess, an ether. It's a stationary frame or an absolute reference frame, if you will.
Yeah, it is.
Okay, that's good.
It's an absolute reference frame, actually.
So could we say then that excess electron-positron pairs, if let's say the Epola that you hypothesize is full, so that means if there are excess electron-positron pairs, they have to be something else, such as protons or other particles. Is that a fair evaluation here?
Yes. Yeah, that's a fair evaluation.
Oh, okay, Mark. Does your work or the work of others that you're talking about account for the three generations of particles that are generally recognized?
No, not really. I don't believe that those are real objects. I agree with Mary Gelman's suggestion that they're just mathematical constructs.
The quark.
Quarks. Oh, and the three
finally,
generations, the muon and the tauon. Sternglass has a model for the muon as an electron-positron pair and an unpaired electron or a positron. And the tauon is the same way. It's a pair and a third one. The muon, the third one, is on the outside, orbiting around it, and the tauon, it's on the inside.
Okay, just a couple more questions, if I may. What again now is the size of the little boxes?
7.62, the lattice length, 7.62 Fermis.
7.62 Fermis. And in other words, that's a factor of 10 greater than the generally accepted size of the proton.
Yeah, the proton, the generally accepted size is about 10 times smaller. Right.
Okay.
So proton's got plenty of room to go inside one of the boxes.
Why are the electron-positron pairs at the vertices of the box? I assume there's 8 of them to form a box?
Yeah, eight pairs form one box.
Why do they have this 7 odd Fermi distance between them?
Well, I got that.
Why is it not
read
some other value?
Theoretical work by Sternglass and Shimon. You can read that. And essentially how I do it is I calculate the size of the universe and the amount of the mass of all of the Epola that's in the universe, and compare that with the mass of the universe. And the ratio I set it equal to this ratio that Sternglass calls the Dirac number, 4.2 times 10 to the 42. Or no, it's the square of that. The square of the Dirac number, which Sternglass calls the Eddington number. It's that I set it equal to that ratio. According to Simhony, it's very close to that ratio. Well, I set it equal to that ratio, and that makes the distance a little bigger than Simhony's distance, about twice, almost twice as big. And that's how I get that length. It's a hypothesis. It's similar to the one that Sternglass uses to calculate the mass of the universe. He uses that same ratio in his calculation of the mass of the universe as a hypothesis. He uses it as a hypothesis.
Question has put in, how is the EPL detected or observed? I suppose, gentlemen, none of this is observed directly. It's really a model, which
actually it is observed. Actually, it is observed. It is observed directly.
Well, how?
This particles they've discovered. They're called. There's three of them. They're called the bottom lambda, the bottom sigma, and the bottom xi. There's three so-called particles. They're almost exactly the same mass. And that's in my paper. I think that's in the Larmor precession. It's in one of them, where if you calculate the size of the elements that compose the Ebola. Now, when you use an electron microscope to look at something small, the electron microscope can see only objects which are larger than its the de Broglie wavelength, which is easy to calculate. It's based on the relativistic mass. So the faster the electrons are traveling in a particle accelerator, the smaller the de Broglie radius or de Broglie wavelength, the smaller it is. And you can see particles only that are larger. So in order to be able to see something as small as they're very, very small, the elements that compose the Ebola, they're about 17 times smaller than a proton or a neutron, very small. They're the smallest objects in our universe. To be able to see one of them, you would need electrons with a certain amount of kinetic energy. You can calculate that amount of kinetic energy. It's exactly equal to the mass of these three so-called particles. They're not particles, they're vibrations of the Ebola that when you speed electrons traveling at almost the speed of light causes the boxes to vibrate in a certain way that gives the appearance of particles. They're not really particles because they last for so a short length of time. They're just little blips of energy. So those three that I mentioned, the bottom sigma, the bottom lambda, and the bottom xi, actually evidence that researchers have already seen some of the elements that compose the Ebola, but they don't realize it because the Ebola, the Standard Model denies the existence of any kind of ether or ether-like substance in our universe. So that's a proof that we've already seen. And those elements I mentioned, the bottom sigma, those three, the bottom sigma, the bottom lambda, and the other one, they're the most massive elements in the list, except for one, which is slightly more massive. And if you look at a list of mesons, those are baryons, unstable baryons. If you look at a list of unstable mesons, it's the same thing. The largest in the list are just about that, in that range, except for one that's about twice as large. So those things are not really element. They're not really objects. They're little blips of energy that you get from shooting high-speed electrons through space.
Okay. There are some comments, by the way, gentlemen, coming in disagreeing with a lot of that, you know. Okay. Didn't realize you could see anything directly and so on. Yeah. And then just a simple counter. Okay, well, it's a model.
It's not a soup. A soup is liquid. It's a solid. It's true. A pole is not an electron positron soup. It's a solid. It's not liquid.
Okay, well, I'd be interested to hear whether George James Dukas intended that when he used the word soup. Okay, that's an interesting comment. Right. Well, you know, we've looked at a lot of angles of this subject. Jim, anything else you'd like to say at this stage to Mark?
Well, a final question might be: does this work account for the measured value of vacuum light speed? Does this work? You know, the what you're presenting account for the measured value of vacuum light speed?
Well, that's already accounted for by a very simple formula. The speed of light is equal to the square root of the binding energy divided by the mass. So the binding energy of one of the electron-positron pairs, the amount of energy you need to knock one loose from the lattice, is known. It's equal to the 2 times the rest. It's equal to the rest mass of 2 electrons, the energy of 2 electrons. And the mass is 2 electrons. Or no, the mass is 1 electron. Each of the elements of the polar weighs the mass of 1 electron. So you take the binding energy, divide it by, or maybe it's 2 electrons, but it's a very simple formula that gives you the speed of light. It'll give you the speed of light. C equals the square root of energy, binding energy divided by mass. Same as the speed of sound, I believe.
Well, but the mass is another unexplained observation.
Yeah, we hypothesized.
So you can't account for an unexplained observation by citing another unexplained observation. I mean, that's not science.
Yeah. Well, it's all just it's
So
theory.
I guess the conclusion we're left with is the work does not account for the measured value of the speed of light. It's like some people also say that the Maxwell work accounts for the speed of light, but that also depends upon the electric charge value. So that again, people are running around in circles, saying that they get one explained observation accounted for by the measured value of another unexplained observation. You see the point there? Wouldn't it be a better idea to actually look for some postulates which actually might yield an account for why the measured values are what they are for any of these so-called fundamental constants?
Mm-hmm.
That's just my 2 cents. That's just my view on it.
Yeah, you don't want to rely upon
Apparently, other people are happy with
constants.
saying that they can explain one fundamental constant by using some equation containing another unexplained value.
Mm-hmm.
And everyone's quite happy. But I don't think they should be happy.
No,
they
it
should
was
be
an
saying,
experiment.
it's going around in circles. We can't explain any of it.
There was an
Any of
experiment.
it at all cannot be explained.
There was an experiment that was done in 1931 where they
Go ahead, Mark.
They created electron-positron pairs from photons, and they knew that the energy of the photon, and they know how much energy you need to create a single electron-positron pair. And then you take that energy, divide by the mass of an electron-positron pair, and take the square root of it. And that's the speed of light. That was this experiment in 1931. Supposedly, they call that it's the opposite of annihilation. What do they call that? When it generates an electron-positron pair production. And Simhony says there's no pairs that are actually produced. It's just an electron-positron pair is knocked off of the internet.
Well, there again, you just said what I said. You're using the mass, an unexplained value.
They measure the value. They measure the binding energy. No, they measure the value. They measure the binding energy, and they measure the mass of the electron-positron pair, and they divide and they take the square root, and that gives you the speed of light.
You're more concerned, Jim, with the fundamental nature of say mass, which is taken to.
Well, I guess the realization I'm coming through in sessions like this is that people are quite content to take one unexplained measurement and use it to get through some formula another unexplained measurement value and think that they've derived it or something, rather than simply going around in a world of everything being unexplained, which appears to be, to me, a more realistic view of the situation.
Yeah, well, that's your
I don't know how to say that anymore.
You're entitled to it.
Yeah, well, I think we can usefully come back to this, particularly between you two gentlemen, because you have complementary or supplementary or contradictory or ideas coming together, and I think we need to hear Jim. What you started telling us at the start of this talk. I think we might come back to this and get a fuller presentation from you. Have a look at the video and some of your materials, and then in the light.
Well, actually, Mark and I, if I may add to on a more pleasant note, Mark and I really agree on a great many important concepts, like, for example, the presence of a lattice comprising what we might call a stationary or preferred or absolute frame, so that my work and his work, as he's explained it, are in agreement on that subject. And so that there's plenty of area of agreement. It's just that I'm beginning to realize that our question why people are happy with thinking that using one unexplained observation to account for another unexplained observation is getting anywhere.
Mm-hmm.
Okay.
Yeah, I understand that you're concerned.
Well, thanks for that. I think we're going to have to give that some more thought. We are running a bit out of time, and there may be one or two people in the green room I'd like to bring up. So unless you have anything else quick, Jim, perhaps.
Oh, no, I'm fine. I love you all.
Thank you very much indeed.
Thank you, Mark.
Mm-hmm.
Okay. Now, Cornelius is there, and if he has the media, the audio and the video, because they're both off at present. Maybe he's not there. Oh, he is there. Yeah. Well, if you could give us the benefit briefly, because we're running out of time, Cornelius, of your take on this whole question of Epola and the explanation of gravity and Mark's ideas and whether it's a model or whether we've actually seen this structure.
I'm not sure if you can hear me or not.
Yeah, you're a bit low, but I can hear you.
Okay, I'm trying this on a cell phone, and I'm actually donating blood at the time. So, but my view on both of these models, both Jim's and Mark's, and actually Simhony's, and is that basically they are all models that are used to basically quantize the amount of energy distributed throughout the ether. In my view, the ether is a continuum of tension field. Because even in these models, in the Simhony models, and that you have an electron and a positron that are generating an attraction and a repulsion from each other. But they attract and repel each other through a field that's in between them. And so there again, you have to have what's the media that's carrying that attraction and repulsion field. So you're using an electron and a positron to quantize the amount of energy in that area of space in the ether is. And the same thing with Jim, he's using different parts of his cubical model to say this is how much mass you've got, this is how much velocity you've got. And again, he's quantitizing an area of space. And it's all about modeling and how we can use that to simulate the characteristics. But they kind of fall short in the fact that, then you still have to find, you got real matter and you've got this artificial, you've got this lattice structure. And when does the lattice structure become the real matter? And you're not consistent throughout the entire model, because it's only modeling certain specific characteristics of it. And each model is basically taking its values from measured daily, from actively measured systems, from our real world. And they're saying, well, this is how far apart these electrons and positrons are. Or if you're doing it Simhony's, it's an electron-positron pair. There's a question of why is it even needed to be, and I think this is what Mark asked himself too, is why do you even need to have an electron and positron lattice when you can just have a lattice? All you're concerned about is the amount of energy between those points in the lattice, the tension energy. And if you look at there's the bond energy, and everything is about bond. So even the electron and the positron, what's holding it together? So I go much deeper, and I go into it's just simply a bond energy, and it's a a dynamic pattern of waves that create those bond energies that create the particles in that. So
and you don't ascribe a physical model to it per se, really.
Exactly.
You talk about its properties.
Yeah, it's the physical model to me is the wave patterns. So the physicality of anything is come down to a focused wave pattern as a particle. A traveling wave pattern is a light wave, and you have the transverse waves and longitudinal waves, and a combination of the two and moving different directions to make all the material things we observe can come down to different patterns or waves in a continuous bond media. So
you seem to be in a public place, Cornelis. A bit of noise coming in.
Yeah, I'm in a public place. Like I said, I'm donating blood at the time, so there's several people around me.
Okay.
So anyway, that's my take on it. They are models. They are useful models for quantitizing the amount of energy in space, and then because of that, they can make predictions. But they take their size and shape by making measurements and saying, well, this must be how close they are because this is the reaction we see between particles. So they're useful models, but they are neither one of them has a physical existence in that my view. So that's about all I had on the topic.
Okay, well, have you any brief response to that? Maybe looking at more the aspect of these things from the point of view of tension in a medium.
You said it's a tension field, right, Cornelis? A tension field?
The bond energy, tension field, bond.
Tension field, yeah, that's it, right? Because according to my theory. It's magnetic fields hold the lattice together, which is Shimon says it's electromagnetic fields, electrical attraction, but in my model, it's magnetic attraction because uh, you can imagine the three
Yeah.
perpendicular directions, and each one is a magnetic, a line of magnetic force. You know, they go this way and this way. They're next to each other.
Right.
One's next to each other, going opposite directions. Magnetic fields, cylindrically symmetrical magnetic fields, and they go like this, and like this. So that's six. They're pointing in six different directions, and they're symmetrical, cylindrically symmetrical magnetic fields which compose the lattice. You can visualize the lattice as being composed of nothing but, like you said, tension fields, magnetic tension.
Well, you have magnetic tension, but I'm already saying, well, a magnetic field is a pattern, is a wave pattern, and a rotational wave pattern at that, because a magnetic field has polarity, and the ether has no polarity. It's homogeneous, and it doesn't have any particular direction.
Cancels. It's so close. The opposite polarities, they're so close together, they cancel. But you can't measure the polarity but actually it does have polarity. Light is polarizable. That proves that it has that perpendicular kind of polarity.
It proves that light is a transverse wave because it has polarity, but it doesn't prove that the media itself that the light is transferring with is polarized. It says the light wave is polarized, but not the media.
The medium itself.
Yeah, the medium itself doesn't have to have polarization. It just has to.
Well, I think it does. I think it's going. Yeah. They're going. The polarization is so the opposite poles are so close together they can't measure them. I think that's more like.
Yeah. So. Yeah. Again, it's a model.
So in that sense, they cancel.
So, in my view, like I said, it's entirely different. It doesn't require a pre-polarized media. Mm-hmm. It actually accounts for the polarization of particles in that by the method of by the direction in which the waves rotate around a central point. That gives you a magnetic field. And actually, it's
they rotate around a central point. Yeah, the electron-positron pairs creates a magnetic field. Each of the electron-positron pairs has a magnetic field like this planet Earth's magnetic field. So that's what creates the lines of magnetic force throughout the lattice.
So, gentlemen, we are rather running out of time. And before wrapping up, I'd like to give Jim Harford an opportunity of perhaps coming in again. Because he was in at the beginning, and I know he has some context. So thanks very much, Cornelis. Thank you for that.
Thank you.
So I'll just get icon. So just Jim, if you're still there, you did. I'm still. You did help us give us an indication. Having listened to Mark, perhaps you expected to hear a lot already. Has anything you'd like to say in summary before we close things?
Well, Mark has made an incredible impression on me, and as a non-mathematician, and he keeps repeating his work should be understandable from high school math. What you're discussing is really extraordinary, and do I understand the math? I don't know. It's over my head, but I really appreciate the effort that all of you are making to describe the small and the great accounts for the energy in the universe. That's all I can say. I'm really appreciative of all the work you guys are doing, and I'm glad that you're recording this, because I think Mark's work should be recognized, and I hope to see him again, either in Arizona. I may come by.
Well, I'm in Delaware now. Hey, Jim, we can get Jim.
Yeah.
I'm in Delaware. You can take the train down.
See,
Oh,
he's
well,
getting as well in your system.
You have a car? You have a car. Why don't you drive down here to New York?
All right. I thought you were in Arizona again.
No, I've been in Delaware for the last 3 months.
All right. All right. Well, I hope to do that, and we'll contact each other outside.
All right, we'll get together.
And for those who are viewing this on the recording, I left a Vimeo address in the chats. So I don't know if when you publish
Jim help me make about 14 videos. They're all on Vimeo.
so we have several of his lectures.
And maybe we can get rid of that echo for the next time if you're in. It will help a lot. But thank you very much. Thank you.
All right.
Good to see you again. Thank you for your comments on Mark's work.
And we need to blow the ship out of the water with the standard model.
So, Mark, before I close the meeting, anything else you'd like to say?
Yeah, I just want to say we need to, all of us working together, we can and we should very soon blow the standard model out of the water, because the standard model just doesn't make sense on so many levels. It's ridiculous.
Okay.
That's what I want to say. We all should push as hard as we can to blow their ship out of the water.
Because a lot of our work, and certainly my work, is perhaps aimed at blowing the standard understanding at the macroscopic level of the universe. And you're looking at the microscopic level. So I think these things are complementary. Okay. Well, I'll bring you down, and I'll express our gratitude to you in closing the meeting, and thank you very much for all that. Well, you're very welcome. It's our pleasure. And so I just like to thank Mark very much for having given us the opportunity to listen to 2 sequential lectures. I know we have a week in between where there was nothing, and there was nothing last week. We ought to question much further as well. Well, unfortunately, we've run out of time. But anyway, thank you. It's just one of the comments came in. So he's given us 2 lectures in sequence on the work of Sternglass and Simhony. I think I'm pronouncing it correctly now. And I think these are 2 researchers whose work needs to be studied in more detail. Perhaps, I've only had a glancing reference to them, and I've looked at some of the information, but I haven't looked at all the papers. And Mark is a very prolific writer. I know that because once you get onto his email list, he sends you plenty of information, which you have to select really which parts to look at. But he's an incisive thinker, and we're very glad to have him, particularly because of what I said, the complementarity between the macroscopic, the cosmological aspects, and the everyday size phenomena as against the microscopic, the subatomic level. Now, Roger Anderton, as you probably know, is convening the other weeks. There was nothing last week, but he's convening the other weeks, and I think he has a long series of talks and videos concentrating again on what he claims to be the lack of clarity of Einstein's theories as to what they are. So he'll be coming into those in the coming weeks, and in fact, I think he's coming back on one of my sessions, I think possibly the next time. So again, just keep an eye out for the information. So, on behalf of the John Chappell Natural Philosophy Society, I'd like to thank all of you in the social media. I'm sorry we may not have got to all your comments. I see some comments and questions there. We've tried to distill maybe the essence of many of them, but we've missed some of them. And those are things we can deal with again by email or by other means. I'd like to thank Jim as well for having stepped in and really agreed to step out. And I think we're looking forward to hearing some of those ideas again in relation to things like the heat of the moon and effect on gravity and things like that. And last, but of course not least, our speaker today, Mark. And unfortunately, I think it may have been partly our responsibility for not having updated that link. It gave a link to the last lecture. It may be a function of his not being a paid up member or something of the society or not getting information. I don't know. Anyway, we solved the problem ultimately. It did curtail the lecture a bit, but we were able to have a bit of a preview of it or a pre-consideration of some of those aspects. So again, our hearty thanks to Mark for taking the trouble of getting into the system, a system which he hasn't used before, for giving us 2 sequential lectures, and for having been such a jolly good sport in dealing with the questions. So without further discussion, I'll stop the recording now, which takes just a moment. And I'll wish you all, wherever you are in the world, a very good day, and thank you very much for your participation.